see the kinetic energy for the wave. Here we will do the kinetic energy that there is in a wavelength. So let's suppose that we have a volume of air, and around this volume of air, this would be a minimum volume. We have the kinetic energy is 1/2 of the mass times the square of the velocity. The velocity is the first derivative of the distance, but because our equation for the wave is y equals to a cosine of kx minus omega t, the derivative with respect to time, actually it is a partial derivative, because here we have two variables. So the partial derivative of y with respect to time, that is the velocity, is this would be omega a sine of kx minus omega t. This will be the velocity. And the mass, because it's a very small volume of air, let me call that the mass is Pm. So I have that the kinetic energy is equal to 1/2 of mass. Remember that mass is, I have density is mass per volume, so I have that mass is density times volume. So density times volume times the velocity, that is omega a sine of kx minus omega t. Then the kinetic energy is the same as the volume. Let me put it as, I can have some delta x here of y times the or of height, whatever, times the cross-sectional area, or for example in the cylinder, delta x times the cross-sectional area, whatever it be. So I have 1/2 of the density times the area times delta x times, actually here let me put another letter in order don't confuse a and a, so s. So times, oh sorry, here I forgot the square, so I have times omega square s square and the sine square of kx minus omega t. So the kinetic energy, the total kinetic energy in a wavelength would be the integral from 0 to the wavelength of this, and when we are approaching to the volume to be very small, that is when delta x is very small, that is also we are taking the limit as delta x approaches 0. So we have 1/2 of the density times a times omega square times s square times the sine square of kx minus omega t. Now it is not delta x, it is dx, because I'm taking the limit as delta x approaches 0. Alright. So let me take out the constant, and I just have the kinetic energy of a wavelength is the same as the integral from 0 is the density times the area times omega square times s square times the integral from 0 to lambda of sine square of kx minus omega t dx. Now if we are talking about t equals 0, so at t equals 0, we just have now the kinetic energy, the kinetic energy of a wavelength is the density times the area times omega square s square times the integral from 0 to lambda of sine square of kx dx. So this is a little bit complicated to take the integral of some square function, but remember the angular identity formula. We have sine of 2x is the same as 1 minus 2 square sine of x. So I have sine of 2x minus 1 is equal to negative 2 sine square of x. I divide everything by 2 and I switch signs. So square sine of x is the same as this. So let me just do this part here. I have the integral from 0 to lambda of 1 minus sine of 2x divided by 2. Actually here I put x, but here if you see we have a square sine of kx, not a square sine of x. So let me change it here to sine of u. So here I have 1 minus sine of 2u. Now I think that is easier if I substitute u now. This u is kx. And this would be equal to 1 half, just the integral of 1 half, dx is 1 half of x minus, here I think that the easiest way is, sine or negative sine is the derivative of cosine. So cosine of whatever I have here, 2kx, certainly divided by this 2, but also divided by, in this case, is 2k. So this is, this goes from 0 to lambda. This is for k. But anyway, let me check that the derivative of this is exactly this. So derivative of cosine of whatever it be is negative sine of whatever it be, 2kx, times the derivative of the inside, the derivative of this with respect to x, that is 2k, divided by this that are just constants. I kill the case, these 2, and so I have negative sine of 2kx divided by 2, negative sine of 2kx divided by 2. Alright. So, now we have that, we're evaluating this. So, we have 1 half of lambda plus cosine of 2. Remember that k is the linear wave number. K is 2 pi divided, or 2p divided by lambda. So cosine of 2 times 2p divided by lambda times lambda. X is taking the value of lambda, divided by 4k, minus 0 plus cosine of 0 would be just 1, so 1 over 4k. So let me see this expression. Here I will cancel the lambda, and here I have cosine of 4p. Cosine of 2p, 4p, 6p, whatever it be, is just 1. So I have 1 half of lambda plus 1 over 4k minus 1 over 4k. This is just 1 half of lambda. So I have this expression would be equal, or the kinetic energy of a wavelength is the same as 1 half times the density times the area omega square s square times times all this, that is, well, this 1 half here and this lambda. And just something that I'm missing here is that here I forgot to put, all the way I forgot to put the 1 half of the kinetic energy, 1 half of the square of the velocity. So here I forgot that everything of this is multiplied by 1/2. So actually here I have 1/4 of the density times the area times square omega times the maximum amplitude square times lambda. And this is the kinetic energy of a wavelength. We will use this to derive the intensity now of a wave.